Welcome everyone to our highly anticipated webinar regarding expressions, part 2. I'm Abri Fasagi from Adroit and Mitsubishi, and I'm here to just elaborate on last month's webinar regarding the bare basics of expressions. So first off, we're just going to start with a short introduction about what we will be covering and where our information comes from. We'll elaborate on some of the Adroit expressions that we use in our Smart UI. We'll take a look at the different types of expressions as well as some examples of how to implement them and what they do. And then we'll be going over to GXWorks, looking into the expressions there. Just a short recap of what Regard explained last month. And then I'll just take you over to a small HMI to give you a decent view of exactly how they work and how they can be used. So this webinar, we will cover the basic principles and provide some intermediate level examples of both Adroit and GTWorks expressions to illustrate their application and gain a clear understanding of the fundamentals and to see how they would work in practical scenarios. These Adroit examples that are being showcased are adapted from the help files that you can find in the agent configurator. And we're just going to elaborate on the GXWorks examples that Regard had last week and just show some of the intricacies that you might find therein. So first off, when looking into examples, you will find into expressions, you will find the following window pops up when you start to edit your expressions. First off, you have value number 99 here, which is the value being edited or being calculated. We have our different variables where you can set up your data from different agents. In this case, we have a analog agent and we're reading the value from it. And in the expression itself, first off, this is considered a single term. Should there have been operands such as addition or subtraction, we would be handling different terms, but for a single term, we can see that we have variables, mathematical functions, and constants or numbers that's just being added. In this case, we can see for a cosine expression that we have a value being read in degrees, but since this cosine function handles radians, we needed to convert it. So we multiply it by pi and divide by 180, so we can convert our degrees to radians. So for the Adroit side of things, when we look at expressions, you can see there's a bunch of different things we can do. We see we have do if true or else functions, logical expressions, which are mainly for computer science, and, ors, nors, nots. We have nested expressions, totalizers, mathematical functions. We can have ramp expressions, control expressions, and prioritization expressions. Where we see also we have angular expressions, power expressions, remainder, exponentation, raising to the powers, and bitwise negation. Now, to showcase this, we have a little graphic form over here that we set up to show you exactly what we have and how we set it up. So first off, looking looking at the do if true. Very standard. We have a single variable being monitored, seeing that if this is true, this digital value becomes positive, we read from an analog value. Should this not be the case, we ask the value to stay the same. To showcase this, we have a little slider over here. Should we change it, you see that our analog value stays the same. But once we toggle our digital value, you'll see that it reads from the slider and the analog value is expressed. For logic, our ANDs, ORs, NORs, and NANDs, you see we have two digital values being compared. On the one hand, looking at AND, you can see that if both are toggled to positive or on, we will be reading a 1. Should this not be the case, our value returns to 0. Alternatively, for an OR, you'll see that we are reading from both, and if either of them are being ticked, we will be reading a 1. Alternatively, if neither would be the case, it'll be reading us 0. Now here we can see that how our logic table works, but for NANDs and ORs, the expression changes a little bit as we add an exclamation mark before our for our values. So we can say we want the inverse of this. We want value or variable 1 not to be selected. Take a look next at a ramp expression. This is very straightforward. Should a digital or a condition be met, we want to take the value that's currently being calculated, and we're just going to add a constant to it. If whatever condition we set has not been met, we just ask for the value to stay the same. So should the value be met, we can see that 0.05 is added to it every second due to how the expression is set up. Next, bitwise negation, also known as bitwise complement. This is an operand that flips the state of each bit in a binary number. So we can see that zeros and ones becomes ones and zeros. We have our most significant bit indicating that we have a sign change. So in this case, where we have a binary number of 4, once a certain condition is met, we take a bitwise negation, which we can see by the symbol here. If that's not the case, we hold the value as it is. So should the condition be met, we can see that it changes to our bitwise negated value or complemented value. For a nested control, this is one where a lot of people struggle when dealing with large amount of numbers. So for this example, we assume we are looking at a bunch of tanks running into a single container, and we can control the amount of each tank that we are supplying. So if we were to say we want values from all 3 tanks to be considered, we would calculate that we would have 19 kilograms or units of mass expected in the final container. However, we would just remove 1, see that now, since we're not including ingredient 2, we're just expecting a mass of 14. Now, however, over here you can see that we have a value that's currently just reading from ingredient 1. This is because as the expression is set up, it's still considering all the different values from the above expression. But since we're only checking to see if digital 1 over here is being considered, once we see that this condition is met, we read the value and we ignore the rest of the expression. So although we see ingredient 1 and ingredient 2 is being considered or is expected, since ingredient 1 is the first one seen, it just gives us a single output from this part of the expression and ignores the rest completely. Next, looking at angles, we have a series of trigonomic functions from sinus, cosine, tangent, all the way over to the hyperbolic sine and arcsine functions. Now, just as seen in the previous expression or in the previous slide, we have a mathematical function over here. We call a variable, which we will see here. And since we're reading it in degrees, we need to convert it to radians since our function expects radians. As we toggle the value and we increase it bit by bit, we can see that we are currently reading for a sine value of 30 degrees that we will expect a value of 0.5. And as we keep increasing them, we can see that we have calculated our trigonomic values using Adroit expressions. Next up, power and exponential expressions. For this, we are reading from these two expressions over here. Adroit also accounts for power 3, which is x raised to the power of 3, as well as the exponential value over here using Euler's number and raising it to a power of x, which in this case comes from variable 1. We change this value, we can see as x changes, each value is converted or calculated to the power of 2, as well as Euler's number being raised to the power of x that we have here. Finally, for the Adroit side of things, we can see that we have prioritization. Now, prioritization involves assigning different levels of importance to bits based on their position in the binary value. So by modifying this using this operand over here, you can see that our expression currently calls that for value 1, as long as it is smaller than the value of 60,000, we want this value to constantly be shifted 1 to the left. So in this case, if we look over here, having a value of 4, this would have shifted the 1 over here, making this value 8. If we have shifted it twice, the 4 would have become a 16, and if we shifted it 3 times as expected here, the 4 would become a 32. Now, this can be seen once we activate this. You can see that this value keeps multiplying by 2 as expected for a single shift in the binary bit. We see this one being multiplied by 4 for every 2 positions it's being shifted to the left. Over here we can see the exact same happening, but multiplied by 8 since it's moved 3 positions to the left. If we had flipped these from less than signs to greater than signs, we would be dividing by 2, dividing by 4, and dividing by 8. And these are not limited to just 1, 2, and 3, but for this example, we are mainly focusing here. Next, for the GXWorks side of things, quick recap. We see the $sign is used to represent a string, which is used here to store text data. And this will be stuff like addresses, names, passwords, etc. On the other side, $W and $V both represent variables. The main difference here is that the $W represents weights stored in words variables, and thus are only used to store larger numerical values. So since these represent the same, words are only used to store larger values. Now, just a quick recap as to how the expressions are set up. First, we will see the data expression over here. This is the final expression expected from how you're setting it up further down in the edit expression window. So first, we start with the style. This is just a combination of the amount of variables we're calling as well as how they will be processed. In this case, we can see that first A and B will be processed as a single value. Next up, followed by C and D being processed before the final answers of A and B and C and D calculated, and then E is considered for the final expression. Now, we have variables A, B, C, and D, which are being inserted from this input variable details here, where we can say we want values currently written from the device itself, constants, or written from other devices or read from other devices. As for these dots in between, these are operators that are being set here. So should we have only chosen A and B, as we'll show in a moment, we only have the option of setting this operand here. And this will be addition, multiplication, division, or subtraction as required. Finally, we have the constant data type, which is how these values, these constants over here, are being read. Considering 12, if we had read this as an octal value, instead of 12, this would represent 10, or in hex, this would represent 18. Since the 1 would no longer be a decimal 10, it would be a 8 or a 16. Now, quickly, if we show our graphic form here, or our form here, this is just a short little example of how values will be displayed and how it works when writing to them. So here we can see that reading from a constantly shifting value, that we have values that keeps increasing as the value increases. Now this is mainly done just by saying we are reading from a device and we are reading it as a real value signed binary 16-bit. When we consider writing values, here we can see things we change a bit. We go to the advanced settings, say we do a data operation, and over here we can set monitor values and write values expressions. So when monitoring here, we can see that for just a single A and B, we are reading from A, which is our device here, and a constant of 55, which we're just adding to it. So checking, looking at value or D203, we'll be reading this value and adding 55 to it, as well as whenever writing this value, we would automatically be reading 55 to it, or writing 55 to it, apologies. This means that for a value 203 over here, we can see that we have no additional operands being added here, operations added. So should we be writing to this value over here, we would see it just shows us a 5. So that's what we entered. But we just showed that we are expecting to monitor 55 above the value being written to DO3. So thus here we see 60. Alternatively, when we write a value of 10, we are adding 55 to it due to the writing expression we added. So we would see 65. But we're also expecting 55 more than that every time. Thus, we see 120 for this expression over here. We see for this specific text value that for monitoring and for writing, we will be taking a value D203. We will be adding 12 to it, and additionally to that, we'll be adding 0.75. But as we see in the expression here, first off, we'll take our value that we have written. We'll add 12 to it, and next operation, we see that we're reading a constant of 0.75. We're taking from value 200, which is seen over here being receiving data from GXWorks, and we are calculating the sum of that. Next, you see in these brackets here, these two values that's just been calculated will then be summed again before the last value, D204, which is being written from here, is added to it as well. So when we take a look at the page again, you see if we were to make this value 0, and as we change D204 from here, that this value is increased by that exact amount. We were to make it close to 100, see there's a jump as it goes past the limit and starts back at just over 100 as it's being calculated. And this is just an example of where our data is coming from. It's on a 16-bit calculation, and it's being scaled over to show us values as we see them here. So this was a very short and brief example of exactly how you would approach these different expressions and how you would approach both Adroit and GXWorks expressions. So thank you for coming to our webinar. If there's any questions, I'll be around for a couple of minutes to answer them. If not, please enjoy your day, and I hope this has been informative.